Hey everybody, it's Mr. Ray here. We're going to start our journey into polynomial functions with an introductory lesson. This is an extremely quick lesson. It's one page. I'm not actually going to do any examples here, but there are some homework questions at the end, and I will be eventually posting the solutions to the homework to all, and that will be for all lessons. Okay, so just a few quick definitions here. So most of these should be very familiar with you. I just want to make sure we're all on the same page. Constant, it's quantity whose value does not change, and these are numbers, which could be integers, decimals, or fractions. Variable is a quantity whose value can change or vary, usually represented by a letter, x, theta, y, etc. A term is a word, mathematical word, and it's created by taking product or a multiplication of a constant and one or more variables. For example, 2x is a term. Negative 3/2 x squared is a term. 24xyz is a term. Okay, so those are terms, and then you take the terms and you add or subtract one or more of them to create a mathematical expression. So it's like a sentence in a language, and the way they're connected is through a plus or a minus sign. So for example, 3x squared minus 2x plus 1, that's a mathematical expression with three terms, and you can just use the plus and minus signs to separate the terms. Okay, and then a polynomial is really just a more mathematical name for an expression. Now, I don't quite buy into this definition. That could be more. It has to be more than one term. I know the prefix poly means many, so by definition, I guess that's true. But I would consider a single term expression to also be a polynomial, even by strict definition. It's not. So, and then the last thing, exponent is the raised number of a variable, or the base that indicates how many times the base is multiplied. Okay, so that should be all review. Nothing new there except for maybe polynomial. So these are the key concepts, and you can see that's all we've got. So a polynomial expression is a series of terms in which each term is the product of a constant and a power of x. Now we could change that variable to something else, but it's important to note there's only one variable, so most of the time it's going to be x. So for example, a polynomial expression, like I said, might be negative 3x to the fourth plus 2x cubed minus 17x squared minus 2x plus 10. Okay, so that's a polynomial expression. It's got 1, 2, 3, 4, 5 terms. Each of the terms has a power of x and a constant that multiplies with that power of x. Now this here, you'll say, well, that doesn't have a power of x. You could put an x to the power of 0 there if you want to be fussy about it. Anything to the power of 0, remember, is 1. So basically that just disappears really. But you could see I've got exponent 0, and this is really a 1. So 0, 1, 2, 3, 4. So I've got 5 different powers of x. When we write the polynomial expression, we always go from the highest exponent down to the lowest. Okay, and like I said before, we probably wouldn't put exponent 1 or x to the 0, but you can see how that fits in. It makes it more you can see the pattern a bit clearer when those are in there. Okay, so this is the formal definition here. You can see we've got, it looks a little strange at first, but we've got our leading term here. Now the a values are the coefficients, so that's the number part. So these could be, if you go down here, they could be any real number, fraction, decimal, integer, but it has to be real. Like you couldn't put pi there. So it has to be a number part. Now, you can see each of these terms has a coefficient part, the a, and you can see here we've got x to the n. So if we've already sorted these from highest exponent to lowest, the n will be the highest exponent, okay? And we actually call, this is listed down here, that's the degree of the expression. So the highest exponent would be the degree. So if I looked at this expression here, this would be a degree 4, a polynomial expression with degree 4, okay? If it's in the wrong order, you have to look for the highest exponent, okay? But normally it would be written highest to lowest exponent. Okay, so you can see the pattern here, x to the n, so you know that's the degree, so in that case that would be a 4, n minus 1, so that'd be x cubed, x squared, and it keeps going down. You can see this dot dot dot, where the last two terms would be something times x plus a constant, okay? Now, do you have to have every single one of these? Now, I had every single one from 4 down to 0, basically, down to the constant. But you can definitely have a polynomial expression where you've left out several of these exponents. For example, negative 3x to the 4th plus 10, that's a legitimate polynomial expression. You don't have to have every single one of these because by the definition here, the coefficient, by the way they've said, is a real number. So could you have a real number of 0? Sure. Okay, so I guess any of these a values could be 0, except really the first one, because if the first one was 0, then your degree wouldn't be n, because it's not really a term. Okay, so this is a special number. We're going to talk more about that as well. Okay, yeah, so a to the n, that's your leading coefficient. We kind of we could put LC for leading coefficient. We're going to be using that quite a bit. And then the final, that's the constant. Okay, now you could have an expression without a constant, but really the constant would be 0 then. Okay, so that's the formal definition of a polynomial expression. So remember, an expression is just several terms added or subtracted together using these rules. Okay, it says x is the variable, but that's, it could actually be any variable that you want, but probably 95% of the time we're going to be using x. Okay, now we go from polynomial expression to polynomial function. So remember, a function is basically, it's an equation where you've got, like a y equals this. So if I wanted to change this expression into a function, in grade 10 or 11 you might put y equals, but we're going to be putting in function notation, so we'll put the f of x in front. So that tells us f of x equals, that tells you it's a function. Of course, that could be a different letter than f. And the rest of this is basically the original polynomial expression. We've just added, f of x equals to the front. Okay, some of this we've covered. The degree of the polynomial function is the highest exponent in the function. Okay, so that would be degree 4. Now, if you're thinking about, have you ever worked with polynomial functions before? You have, because what if you had a degree 2 polynomial function? So that would mean our highest degree is 2, which you could have something like 2x squared plus 4. Have you ever seen that before? Of course you have. That's a quadratic equation. So you've already worked with one of the types of polynomial functions. That would be a degree 2 polynomial function. You've seen lots of those. And if we go back to grade 9 and grade 10 and 11, of course, you could have a function degree 1. So the highest exponent would be 1, so that you could have 7x minus 2. So that's degree 1, and of course that's linear. So you've got quadratic and linear, which you've worked with already. But now in grade 12, we're going to extend that not just degree 1 and 2, but anything higher than that. So we will be doing a lot of work with, we call them cubics. A cubic is the next degree, so that would be something like x cubed plus whatever, anything lower. That would be a cubic. You don't have to memorize that, but if you want to sound impressive, you could say any degree 3 function is a cubic. And if you really want to impress your friends, degree 4, so say negative 2x to the 4th plus 4. So that's degree 4. That's called a quartic. And you can kind of see, cube from, well, that's cubed, right? So the names actually make sense. Quart, I mean, that's, a quarter of something is 1/4. So, and you could look at the names for higher, but we'll rarely be working with much higher than that. But we will look at higher degree, but we won't necessarily have to know the names of them. Okay, so that's the degree. Now this is something that we're actually going to do an example of in the next lesson. So just to give you kind of something to think about, when you worked with quadratics, for example, if you took the second differences of the table of values of a quadratic, you already know that those second differences will be constant. Okay, and from before you knew if you took the first differences of a table of values, and if the first differences are constant, it's linear. Well, that extends into these new families. So if you took the third differences, which is something new, of a function, of a table of value of a function that is a cubic, you'll see that those third differences are constant. And if you took the fourth differences of a quartic table of values, you'll see that those are constant. The fourth differences would be constant. So it extends infinitely. So if you had a 10th degree equation, you'd look at the 10th differences and they would be constant. Okay, so that's actually going to help us when we do some examples in the next lesson. But for now, that's just something to think about, that you do keep taking more and more differences to determine the degree of the function just by looking at just the table of values. Now, here's the thing about polynomial functions, and you're going to look at lots and lots of graphs, but if you were looking at a graph of any polynomial function, it's like a roller coaster, okay? So this roller coaster, it's going to have some bumps and dives and stuff like that, okay? Now, here's the thing about how these polynomial functions end, because you might think, well, that's sort of like a sine curve maybe. Well, not exactly, but sine curves just keep on going the same pattern forever and ever in both directions, where polynomial functions will definitely eventually head towards either negative infinity in the range, or positive infinity. So we know that they're going to head off to some infinity as x goes out. Okay, so they're never going to tail off to a straight line. That never happens. They're never going to approach an asymptote. They're always going to head off either towards positive infinity, like this guy, or negative infinity, like this end. And so we'll be looking at things called end behavior. What is the end behavior of this polynomial? Means what direction does it go to positive infinity or negative infinity in either direction. Okay, so so the other thing about this is, are there any values of x that a polynomial function does not include? And basically this any polynomial function will be defined for any value of x. So even though this is looking like it's almost going straight up, it's still going outwards to the left, and this is going outwards to the right. So eventually this graph will hit all possible x values. So that's the cool thing about polynomial functions. The domain is always the same. It's always all real numbers. There's never any value of x that the function can't have. Now, the range, and we're going to talk more about this in the next lesson. Now, it actually depends on the degree. So, and we're going to learn about the next lesson. You'll be able to tell me whether this is you'll be able to look at this graph and tell me something about the leading coefficient and the degree of the polynomial function. But if I was to use this graph, and you're looking at, does this graph have a maximum or a minimum? It doesn't, because it goes up forever and it goes down forever. So I could never say there's a max or a min for this polynomial. Okay, so that would be true of that type of polynomial. But if I had another one which looked like this, okay, this is another type. This actually does have a maximum. Okay, or if I took another one here, and I'll use a quadratic this time. So if you have a quadratic that looked like this, okay, in this case you have a vertex there, that would be your minimum. So some polynomials have max and mins and some don't. And of course, if you have a max or min, it's one or the other, not both. So that's what this says here. The range of a polynomial function may be all real numbers, like the first case here. So the range is all real numbers. All values of y are reachable, or it may have a lower bound, which means minimum, or an upper bound. So this has a upper bound, which is a max. This has a lower bound, which is a min, but it can't have both. It's one of these three cases where there is no max or min, or there's a max or there's a min. Okay, so covered that. Domain and range. So domain's always the same. The range changes depending on certain characteristics. Okay, and sort of talked about this. The fact that it doesn't have a vertical asymptote means all values. You could figure that out by the fact that the domain is all real numbers, so there's no breaks, and there's no horizontal asymptote, which means it doesn't sort of tail off. Like if something had a horizontal asymptote, it would kind of go towards a certain value like that. So that would not be a polynomial function, because that's a horizontal asymptote. And the functions that have vertical asymptotes, and we're going to do a lot of work with this, something like this, that's definitely not polynomial function, because it has both a horizontal and a vertical asymptote, and there's a break in the domain here. That value of x is not defined. Okay, so that's it. It's just a quick introduction into what is a polynomial expression, what's a polynomial function, what are some of the key characteristics, the degree, the domain, the range, and we talked a bit about the graphs. Basically, it's a roller coaster with no breaks, and at the end it either goes way up or way down in both left and right side. Okay, so there's some homework there to try. So give that a try. Check the postings for the homework solutions once they're up. Okay, have a great day.